Improper integrals. When we define a definite integral, we suppose that the function is defined on a finite interval. By finite interval, we mean the interval of integration has finite length. In other words, those bounds, a and b, were supposed to be real numbers. And we also assume that the function f, the integrand, doesn't have an infinite discontinuity. What's an infinite discontinuity? It's a point where the function either blows up or blows down. That is to say, it's a point at which the function has a vertical asymptote. So let's say this is the function. It either blows up here or blows down, right? So such a behavior is called infinite discontinuity, if you remember that. Okay? So one more time. When we define definite integral, we suppose that the length of the interval is finite and the function, the integrand, doesn't have such discontinuity within that interval AB. In this section, we're going to actually extend the concept of a definite integral that we've learned before to the case where this is no longer the case. So this is, now we're going to assume that we're going to consider cases where the length of the interval is infinite. And also we're going to assume cases where the function may have infinite discontinuity within that interval AB. Okay? In either case, the integral is going to be referred to as an improper integral. Let's start by discussing the former type, which is integrating over an interval which has infinite length. So let's say this is the xy plane, and let's consider the function 1 over x squared, so something like this, for x bigger than 0. Certainly this function is symmetric with respect to the y-axis, so it has another piece on this side, but let's consider only the piece for x positive, and let's consider the area or the region that lies under the curve of 1 over x squared and above the x-axis and to the right of the line x equals 1. So technically I'm talking about this region that you see here that's shaded in orange. You might think, since this region is unbounded, it's infinite in extent, right? It's unbounded, so it keeps going forever. You might think that this area is also infinite. But let's take a closer look. So let's say I truncate this at a fixed number, let's call it t. Okay, so let's take a t be bigger than 1. So some number here that's fixed. Okay, so let t be bigger than 1, be fixed. So we fix it. And then let's consider the area, let's call it the black area. So let's consider the area that's bounded by the curve, the x-axis, and the two vertical lines, x equals 1 and x equals t. So technically, that's the area I'm talking about. Certainly, it's going to be a function of t, right? Let's call it a of t. So, and let's try to evaluate that. So, given that number t, a of t is going to be the definite integral from 1 to t. Now, I am integrating over a finite, right? Over a finite interval. I'm trying to understand what happens, at least here, and then try to understand what happens when t becomes large. So I get this 1 over x squared, right? I'm integrating 1 over x squared over that interval. And if you integrate this, what do you get? You get negative 1 over x between 1 and t, correct? And what's this? So this is, with the minus, you can reverse the bounds. So you get 1 over 1, so 1 minus 1 over t, right? So you get this, this number, 1 minus 1 over t, being the area that lies under the curve, above the x-axis, and to the right of x equals 1 and to the left of x equals t. Okay? And look, this number here, 1 minus 1 over t, because t is positive, this number is smaller than 1 for sure, right? And this is for any t. No matter how large t you choose, this number is always smaller than 1. So the area no matter where you truncate it is gonna be smaller than 1. So it's a little against intuition. And let's take the t and try to increase it indefinitely, which means let's try to let t go to infinity. So this black area becomes technically the orange area. And let's see what happens. So as t increases, so as t goes to plus infinity, what happens to the area? Well, no matter what t is, the area is given by this number. As t increases, as t goes to infinity, this number is going to keep shrinking and shrinking, right? And hence, the area is going to approach 1. Because this goes to 0 as t goes to infinity, and as such, the area goes to 1. Correct? So this area, this orange area, is technically 1. All right? And because this is a finite number, so because this unbounded area is actually a finite number, we say that the area of the infinite region is equal to that number, and we write that this area, which is to follow suit with what we used to do at the level of definite integral, right? We used to write the bounds of the area and the function here. So the bounds are now 1 infinity in some sense, right? Just to keep that notation the same, 1 over x squared dx. So this would be the notation of the limit as t go to infinity of a of t, which was 1 to t, 1 over x squared dx. Okay, so this becomes the symbol representing the limit as t goes to infinity of that area a of t. And what was a of t? It was this integral, right? Which is exactly this. Okay. If we use this example that we just did as a guide, we can define the integral of a function. In this case, we took the function to be a positive function. If we're gonna define it for a general function, it doesn't have to be positive. So we can take the integral of a function over an infinite interval, like here, over an infinite interval, to be the limit of integrals over finite intervals, like we did here, because 1 to t is a finite interval, and we took the limit of that to be the integral over infinite interval, right? So this is the next definition on the next page. So let's read the definition. This is the definition of improper integrals with infinite integration limits. So we are integrating over infinite intervals. Part A, if the integral from a to t f of x dx exists for every single t that's bigger than or equal to a, where a is a real number that's fixed, then we're gonna define this improper integral, so the integral from a to plus infinity f of x dx, to be by definition the limit as t goes to infinity of the integral, which is the integral over finite interval a to t f of x dx. Okay, provided this right hand side, this limit exists as a finite number. So if this guy is a finite number, then we define it to be the improper integral from a to plus infinity f of x dx, like we did above. In the previous context, we had a was equal to 1 and f of x was 1 over x squared, correct? In addition, if this limit exists and the function is positive, you can think about this as being the area of the region that lies under the curve of f of x, above the x-axis and to the right of the line x equals a. Okay, as we did in the previous discussion. All right. So how we defined improper integrals over infinite intervals that look like a to plus infinity, we can do the same over intervals that look like minus infinity to b. They're still infinite, but on the other side now. Very similar. So if this is part B, if you have this integral over finite interval from t to b, f of x dx, to exist, if you have this existing for every single number t that's at most b, where b is also a real number like before, where b is a real number that's fixed, then we're going to define this improper integral here from minus infinity to b f of x dx to be the limit as t now go to minus infinity of the integral t to b f of x dx, provided the limit exists as a finite number. Okay? So each of these two is called an improper integral, and we say that such an improper integral is convergent if the corresponding limit exists, right? So we say that this is convergent if this limit exists, and we say that this is convergent if this limit exists. Otherwise, such an improper integral is called divergent, which means when the limit doesn't exist. Okay? All right, part C, so I'm reading this one. If both improper integrals a to infinity f of x dx and minus infinity to a f of x dx are convergent, so if each of them is a number, then we define the integral from minus infinity to plus infinity f of x dx to be the sum of those two. The sum of those two. So from minus infinity to a f of x dx plus the improper integral from a to plus infinity f of x dx. And this number a, so the comment here, this comment is about part C. So this comment says any number a actually can be used, right? Any number a here can be used. Okay? And let's actually discuss this case. This is on page 582. This is a problem. This is actually 107 on this page. So let's copy it. And let's paste it here and do it. So what's the deal here? The deal is this number a can be anything, right? Can be used. Any number a can be used. Let's paste it here. And let's read it. So let the integral from minus infinity to plus infinity f of x dx be convergent. And let a and b be two real numbers that are distinct. So they're not the same. We need to show that the integral from minus infinity to a f of x dx plus the integral from a to plus infinity f of x dx is equal to the integral from minus infinity to b f of x dx plus the integral from b to infinity f of x dx. So that number can be anything. That's the point here, right? It can be a, it can be b, it can be any number that we wish. All right, so let's deal with that. So what I'm gonna do is, since a is not b, one of them is gonna be bigger, right? So let's assume that b is bigger without loss of generality. So without loss of generality, we assume, or we may assume, that b is the bigger one, right? In other words, if actually a is the bigger, just replay this game that I'm gonna do here, where a is replaced by b and b is replaced by a. Okay. So I'm gonna start from the left hand side. So minus infinity to a f of x dx plus the integral from a to plus infinity f of x dx. And I'm gonna write a sequence of equalities, and at the end I'm gonna get to the right hand side. Okay, so what does this mean? What this means, according to the definition that we just read, part C of the previous definition, this is the limit as t goes to minus infinity. I'm talking about this one, integral from t to a f of x dx plus the limit as, let's call it s go to plus infinity, right? I'm talking about this integral now, a to s f of x dx. Okay? And now since b is bigger than a, so b is between a and s, right? If s is large enough, b is gonna be found between a and s, correct? So I can then rewrite this integral here, this one, for a sufficiently large s. This is then equal to, because this is a definite integral, this is an integral over a finite interval. So this is the same as the integral from a to b, right, because b is there, f of x dx plus the integral from b to s f of x dx, right? So this is how we used to do it before for integrals over finite intervals. And we get this. So let me rewrite what we have. So this is then equal to this guy, limit as t goes to minus infinity, integral from t to a, f of x dx, plus the limit as x goes to plus infinity of, we split that as the sum, so integral from a to b, f of x dx, plus the integral from b to s, f of x dx. Correct? So we get that. And this entity here is independent of s, right? This entity has nothing to do with the s. So I can split the limit. So the limit of that is itself. It's a constant with respect to s. And then plus the limit of the other integral, right? So since this guy is a constant with respect to s, I get the limit as t goes to minus infinity, integral from t to a, f of x dx, plus that integral, because this is independent of s as we said, f of x dx, plus the limit of that integral. So far so good. I get this. Right? And what is this again? What is this guy? The limit as s goes to infinity, the integral from b to s f of x dx. This is the improper integral from b, by definition, from b to plus infinity f of x dx, right? F of x dx. So we get this piece, right? We get this piece. So we're missing this piece, and I hope you see it. I hope you see it. Let's actually zoom in and keep working on it. Now we're gonna play the same game that we did over here to actually bring that in to the limit, because this is a constant with respect to t. This has nothing to do with t. This integral, it's independent of the t, right? It's a constant. So I can play the same game that I played the previous stage to transition to this stage, but backwards, right? I'm gonna bring it inside the limit. So I get the limit as t goes to minus infinity of the integral from t to a, right? From t to a, f of x dx, plus the integral from a to b, f of x dx. Correct? Plus that guy, which was this. Okay? And what is that? When t is a number, it's a fixed number, and you integrate over this finite interval from t to a, and you add to it the integral from a to b of the same integrand, what do you get? This is what? Isn't it the integral over the finite interval from t to b this time, f of x dx? Correct? So it's the same game as that, but backwards, right? So we get this. And this is then equal to the limit as t goes to minus infinity of that guy. So this integral plus this piece, right? Plus this piece. And this piece, this integral, since they told us that the limit, they told us that the indefinite integral is convergent, so this means that this is a finite number, and this is denoted by the improper integral from minus infinity to b f of x dx, right? And that guy plus this guy is the desired thing. So let's finalize it. This is then equal to the integral from minus infinity to b f of x dx plus the integral from b to plus infinity f of x dx as wanted, right? As wanted. Why as wanted? Remember, we started from the right side and we transitioned to the left side. This is the wanted side, right? So we started here, and then we transitioned all the way to here, and we showed that they are equal, right? All right. So what can we say then? This comment then is valid. Any real number a can be used, and this is by the exercise below on page. So this is C, problem 107 on page 582. Correct? All right. Let's look at example 1 now. Determine whether the integral from 1 to infinity 1 over x dx and the improper integral from 1 to infinity 1 over x squared dx are convergent or divergent. We know that this guy is convergent, right? So this was shown before. So we showed that this is convergent, right? That this improper integral is convergent. Where did we show that? Is convergent. Where did we show this? We've shown it on the previous page. Let me take you back there. It was discussed here, right? So 1 to infinity 1 over x squared dx was this limit, and this limit was 1, right? This is actually 1 at the time. So this was equal to 1. Remember, this is a of t, right? And a of t goes to 1 as t goes to infinity. So this limit is equal to 1. So we discussed that, and this was convergent, this improper integral. Now the question is back here. Well, how about this integral now? How about this integral? Let's discuss this. So the integral from 1 to plus infinity 1 over x dx. Well, what this means is the limit as t goes to infinity 1 to t 1 over x dx, right? And so we integrate this, right? And then we let t go to infinity. So what's the primitive of 1 over x? It's ln of absolute value of x, right? So we get the limit as t go to infinity ln of the absolute value of x, but x here is positive, it's bigger than 1, between 1 and t, right? Let's keep it this way, between 1 and t. And this is the limit as t go to infinity of ln of t, and t here is bigger than 1, so positive, let's forget about the absolute value, minus ln of 1. ln of 1 is 0, right? This number is 0. And how about ln of t as t goes to infinity? Remember ln of t? This is the graph of ln of t. As t goes to infinity, the function is blowing up, right? So this is going to be plus infinity then. The limit of that guy is plus infinity. Which means that this integral here is divergent. Correct? So this integral is divergent. This is divergent by this discussion. Correct? Let's actually understand a little bit the geometric interpretation of, or contrast this with that, okay? Geometrically. So 1 over x squared, we discussed how the graph looks like. So the graph was like this. for 1 over x squared, correct? And for this integral, technically we are talking about the region below the curve, above the x-axis and to the right of the line x equals 1. So this curve here, this area here, right? Whereas this one, 1 over x, the trend is very similar to 1 over x, right? It's very similar to 1 over x. And we're talking about the area from 1 to infinity, bounded by the interval 1 to infinity. So this area here, right? So even though they look very similar, this curve is 1 over x, but it happens that this is a divergent, this is infinity. We found it to be infinity, while this is equal to 1. This area was 1 at the time, right? So even though the values of both functions, 1 over x squared and 1 over x, decrease to 0, they both decrease to 0, but 1 over x, the values of this function decrease slower than the values of 1 over x squared to 0. And as such, so 1 over x doesn't decrease fast enough for its integral to actually converge, to be a finite value. Okay? All right. So let's now do the second exercise. So let's read the second exercise. For what values of p, for what values of real number p is the integral from 1 to infinity, so the improper integral from 1 to infinity, 1 over xp dx convergent? We have a feeling of how these things should look. When x is 1, it's this one, right? When x is 1, we got divergence, and when x was 2, we get convergence. But now we want to complete the picture. We want to understand exactly for which of those exponents this is going to be convergent. Okay? So let's take this exercise to a different page and treat it there. So this is example 2. So p is a real number, and we want to understand, so p is a real number, and we want to understand for which values of p the improper integral from 1 to plus infinity 1 over xp dx is going to be convergent, right? This is the question. So since we know that from example 1, we know that when p is 1, the integral from 1 to infinity 1 over x dx is divergent. Let's take, since that case is understood from example 1, let's take p to be different than 1. Okay? So since we know that when p is 1, this guy is divergent, we suppose now that p is different than 1. So it's a real number that's different than 1 for now, right? Because that case was understood. Very good. So as such, what's this? Well, how do you integrate this when p is not 1? So by definition, well, first, by definition, this is the limit as t goes to plus infinity, right? 1 to t, 1 over xp dx. All right, now how do you integrate this when p is not 1? The primitive of 1 over xp when p is not 1 is x to power minus p plus 1, right? So the limit as t goes to plus infinity, x to power minus p plus 1 divided by minus p plus 1. And this should be taken between 1 and t. Correct? Again, 1 over xp is the same as x to power minus p, so you are integrating x to power minus p, you add 1 and you divide by this exponent, right? And this is equal to limit as t goes to infinity, t to power, so t to power minus p plus 1 divided by negative p plus 1 minus, when x is 1, you get 1 divided by minus p plus 1. Correct? And what is this? This is equal to the limit as t goes to plus infinity. You can factor out that 1 over minus p plus 1. Minus p plus 1 is 1 minus p, the same thing. So, and t to power minus p plus 1 is the same as 1 divided by t to power p plus 1, p minus 1, sorry. Right? If you want to bring that down, you take the opposite of that exponent, which means p minus 1, right? Okay. Alright, so in our context, p is different than 1, right? This is what we supposed. We said p is different than 1. So there are two cases. Either p is bigger than 1 or p is smaller than 1, right? So let's say case 1. If p is smaller than 1, this means that p minus 1 is negative, right? P minus 1 is negative. That is to say 1 minus p is positive, right? 1 minus p is positive. And if we call this limit L, so L is equal to the limit as t goes to plus infinity 1 over 1 minus p, this guy, but since 1 minus p is positive, I can think about this as t to power 1 minus p by taking it back up, right? By taking this guy back up, which means I'm gonna take the opposite of the exponent, minus 1. And this is equal to what? Well, the exponent now is positive. This exponent here for t is positive, and t is blowing up. So what happens to the whole thing? This is gonna also go to plus infinity, right? So this is gonna go to plus infinity. Since what? Since t to power 1 minus p goes to plus infinity, as t goes to plus infinity, 1 minus p being positive, right? In this context, 1 minus p being positive. Okay. So when p is smaller than 1, this limit is gonna be plus infinity, and as such the integral is gonna be divergent. Correct? So this means the integral from 1 to infinity 1 over xp dx diverges when p is less than 1. Correct? When p is less than 1. I'm talking about this case, when p is less than 1. And also it diverges when p is equal to 1. This is the case we discussed in example 1. I also refer to it here. So when p is equal to 1, this is also divergent, right? So this integral is divergent. I'm mixing up terminologies here, so it should be is divergent when p is smaller than 1 and or equal to 1, right? So when p is smaller than or equal to 1, you get divergence. In this case, we discussed just being smaller, and in example 1, we discussed when p is equal to 1, correct? Very good. And case 2, when p is bigger than 1. So case 2, this is the case when p is greater than 1. Then what can you say about the p minus 1 thing? P minus 1 becomes positive, right? P minus 1, the exponent here, becomes positive, and hence 1 over t to power p minus 1 goes to 0 as t goes to plus infinity. One more time. Why? Because the exponent here, this guy, so this guy here is positive. So 1 over t to power positive, fixed positive entity, as t increases, this is gonna keep shrinking, right? This is gonna go to 0 as t increases. Okay? And hence the limit becomes, this guy goes to 0, and the limit is gonna be simply 1 over 1 minus p times negative 1. Correct? So thus L is gonna equal the limit as t go to plus infinity 1 over 1 minus p. I'm just copying what we had before. 1 over t p minus 1 minus 1. In this case, this guy is gonna go to 0, and we get the limit to be this entity times negative 1, which means 1 divided by p minus 1. Correct? That is to say, the improper integral from 1 to infinity 1 over xp, which we called it L, right? The limit of that is actually equal to 1 over p minus 1 in this case, when p is greater than 1. Okay? So all in all, what do we get? All in all, what do we get? Let me highlight the findings. We got that this integral is finite. This is a finite number when p is bigger than 1. So this integral converges or is convergent when p is bigger than 1. And this integral is divergent when p is at most 1. So all in all, so to summarize, the integral from 1 to plus infinity 1 over x to power p dx converges or is convergent if and only if p is greater than 1, right? If and only if p is greater than 1, which means that convergent precisely when p is greater than 1. It diverges elsewhere when p is less than or equal to 1, right? Alright, so let's go back to the page where we listed all the examples, this page. So we finished example 2. Now we're going to go to example 3. So we're going to evaluate the integral, the improper integral from minus infinity to 0 x ex dx. So that's example 3. We need to integrate or evaluate the improper integral from minus infinity to 0 x ex dx. Okay. All right, so this is what? This is the limit as t goes to minus infinity of the integral, which is over finite interval now, x ex dx. Let's give this guy a name. How about we call it I of t, right? I of t, because it's a function of t. So what's I of t? How do we integrate this? Well, we can use integration by parts here. We can use integration by parts. So let's use integration by parts where or with u prime to be ex and v to be x. So if u prime is ex, u is gonna be ex, and if v is x, v prime is gonna be 1, right? So let's evaluate this integral it. We get uv, so ex times 1, ex times x, so x ex between t and 0 minus the integral from t to 0 uv prime, so ex dx. Correct? And this is what? If you evaluate this at the upper bound, you get 0. Minus, if you evaluate this at the lower bound, so you get t et, minus the integral of ex is ex, and that's going to be taken between t and 0. And what do we obtain? So that's minus t et, right? This is minus t et, minus, if you evaluate this at the upper bound when x is 0, this is e to power 0, which is 1, minus e to power t. Correct? Minus e to power t. So you get at the end of the day minus t et minus 1 minus et. And what do we want? We want to let t to go to minus infinity, right? We want to let t go to minus infinity of that entity which was labeled as it. This is it. So this integral then, so therefore this integral that we had, minus infinity, I'm copying this part, minus infinity to 0x ex dx is simply the limit, right? The limit as t goes to minus infinity of this entity, which is I of t, which we found it to be that guy, right? Minus t et minus 1 minus et, right? And let's talk about each one. So this is the limit as t go to minus infinity with a minus sign outside. T et, I'm splitting them. Minus 1, right? Minus the limit as t goes to minus infinity et. Okay? All right. What's this limit here? As t goes to minus infinity, well, how do you graph et? This is the graph of et, right? This is the graph of et. As t goes to minus infinity, so as t is going this way, the function is decreasing all the way to 0. So this is 0, right? Okay. And how about that? As t goes to minus infinity, this entity here goes to minus infinity. And this guy we just discussed it goes to 0. So this is an indeterminate form of type 0 times infinity. Correct? So I'm gonna use L'Hopital here, but before I use L'Hopital, I'm gonna take one of the functions downstairs. I'm gonna take the et downstairs and obtain. So let's erase this part. So if you take et downstairs, you get minus the limit as t goes to minus infinity, t divided by e minus t minus 1 minus the 0. I'm not going to copy this anymore. Okay. And now if you let t go to infinity, this is still indeterminate of type, this time infinity over infinity, right? This goes to minus infinity, and e minus t, right? Minus t goes to plus infinity, e to something that's increasing, right? This is et. This is et. Or ex. If x goes to infinity, the function is blowing up, right? That's the x this time, and this x is going to plus infinity as t goes to minus infinity. If t goes to minus infinity, minus t is going to plus infinity, and e to the power x, where x goes to infinity, is also going to infinity, right? So what I'm saying is, this guy goes to plus infinity. So this is indeterminate of type infinity over infinity. Now L'Hopital can be applied. So I'm gonna use L'Hopital's rule. And what do I obtain? I obtain minus the limit as t goes to minus infinity. Derivative of t with respect to t is 1. Derivative of e to power negative t with respect to t is minus e minus t. Correct? Minus that one outside. And this is equal to what? This minus with this minus turn everything into positive. 1 over e minus t. E minus t, as we just discussed, as t goes to minus infinity, e minus t goes to plus infinity. 1 over infinity, right? 1 over something that blows up is going to 0. So this is going to 0 minus 1. One more time, why this is 0 again? Because minus t goes to plus infinity as t goes to minus infinity, and as such, this term is gonna go to plus infinity, and hence 1 over something that becomes extremely large is gonna be extremely small, right? It's gonna go to 0. and this is then equal to -1. Correct? So the value of this improper integral, this one, the question, right? The question is actually equal to -1. All right, let's go to that page where all the problems are listed. So we finished example 3. Now let's do example 4. So in this example, we're going to evaluate the improper integral from -infinity to +infinity of 1 over 1 plus x squared dx, right? So since this is a positive function, I can think about this as being the area under the curve, and now I'm integrating from -infinity to +infinity. So if the curve is 1 over 1 plus x squared, it looks like this, something like this. Let me try again. Probably some. It should be symmetric with respect to the y-axis. So technically, I'm talking about this area, right? From -infinity all the way to +infinity. You can interpret it this way. Okay. So let's find that. To find this, according to the definition, we're gonna split it in 2 pieces, right? We're gonna go -infinity to a number a, and from a to +infinity. I'm talking about that guy here, right? I'm talking about part C. So we're gonna split it in 2 pieces. We're gonna stop at a number and then go from -infinity to the number plus from the integral from that number, the same number, to +infinity. And you can choose anything based on 107, page 582, right? You can choose any number you want. And what would be a natural number to stop at? How about 0? Okay. So I'm gonna divide in 2 pieces, from -infinity to 0 and from 0 to infinity. You can choose any number you want, but again, I'm gonna choose a convenient one. 0 would be convenient. Okay, so let's take this example to on the next page. All right. I did a mistake here. It's just a small sign I have to change. This is actually a plus, and this becomes a plus, but the value remains the same, right? Because it's +0 as opposed to -0. Anyway, so it's just minus times the minus. I kept it as minus. Obviously, it's a plus. All right, so example 4. We're gonna evaluate, as we said, from -infinity to +infinity, this improper integral 1 over 1 plus x squared dx. And the way I'm gonna do it is I'm gonna stop at 0, -infinity to 0, 1 over 1 plus x squared plus 0 to +infinity dx 1 plus x squared. Okay, so I'm gonna find each one separately, and if each one is finite, then we're gonna then the value of this improper integral is gonna be the sum of these 2 finite numbers, and hence it's gonna be convergent. If any of the 2 is not finite, then that's gonna be a divergent. It's gonna be a divergent integral, right? So let's give those 2 guys names. How about calling them 1 and 2? So this is 1 and this is 2. Let's start with 1. So let's start with 1. It's the integral from -infinity to 0 dx over 1 plus x squared. And this is what? This is the limit as t goes to -infinity, right? This is part B of the previous definition. Integral from t to 0 dx over 1 plus x squared. Correct? And what's the primitive of 1 over 1 plus x squared dx? And this has to do with arctan, right? So limit as t goes to -infinity, arctan of t. Correct? Arctan of t. Arctan of x, I should say. Arctan of x. And this is between t and 0. Okay? And that's equal to limit as t goes to -infinity of arctan evaluated at 0 minus arctan evaluated at t. And what's arctan of 0? That's 0, right? So you get minus the limit. Why minus? It's because of this, right? It's 0 minus that, so it's minus the limit as t goes to minus infinity arctan of t. Okay, and as t goes to minus infinity, arctan of t goes to, let me remind you of the graph of arctan. So arctan had two horizontal asymptotes, right? Two horizontal asymptotes. The two lines, let's call the horizontal axis the t-axis. So t equals minus pi over 2 and t equals pi over 2. And the function looks like this, right? Something like this. Okay. So arctan of 0 is 0, and as t goes to minus infinity, as we're going this way, the function is getting closer and closer to minus pi over 2, right? So that's going to be then equal to this minus, and that value is minus pi over 2, correct? So whose minus pi over 2 is this value right there? One more time. Why? Because this is the, just see it graphically. As t, this is arctan, this blue graph is arctan. As t goes to minus infinity, the function arctan is going to minus pi over 2, right? This value. Okay. Let's erase this guy. So then, minus the minus becomes plus, right? So this is plus pi over 2. So I, or 1 is finite, right? And hence it's convergent. So this guy is convergent. I'm still betting on this. If this is convergent, then the sum is gonna be the value of that improper integral. So let's go to 2 now. So 2, which is the integral from 0 to plus infinity dx over 1 plus x squared. And this is, by definition, this is part A of the definition, limit as t goes to plus infinity of the integral from 0 to t dx divided by 1 plus x squared. Same thing as before. This is arctan of x. So the limit as t goes to plus infinity arctan of x taken between 0 and t, which is the limit as t goes to plus infinity arctan of 0, right? Arctan of 0, which is 0. We discussed this here. Minus, sorry, it's the other way. Arctan of t minus arctan of 0. So arctan of t minus arctan of 0. Right? So arctan at the upper bound minus arctan at the lower bound. And arctan of 0 is actually 0, right? So this is 0 as previously discussed. So we get the limit as t goes to plus infinity of arctan of t. Right? And if you want to revisit that function arctan, well, as t goes to plus infinity, arctan is going to pi over 2, right? The other horizontal asymptote. Okay? So it's going to be pi over 2 then. Which is also convergent. So 2 is convergent and 1 was convergent. So their sum, the sum of these two values is actually this guy. And each of them happened to be pi over 2. So at the end of the day, the integral from minus infinity to plus infinity dx over 1 plus x squared, which was 1 plus 2, right? We labeled the integrals 1 and 2. It's pi over 2 each. So this is pi then. So this integral is pi. So that area that we discussed on that page, so this area here is actually happened to be pi. this area under this curve. It happened to be pi. Let's now move to the next type of improper integrals. If you remember in the beginning of the section, we said, so there are two types of improper integrals. Either we integrate over an infinite interval, and this is the first type that we just discussed, or we integrate a function which has infinite discontinuity on that interval which has a finite length. And infinite discontinuity, if you remember the definition, it was it's where a function blows up or blows down around a value, right? So at this point we're gonna have a vertical asymptote. The function is gonna have a vertical asymptote. Okay, so let's discuss this case. Let's go to a clean page, and let's say this is the x-axis, and the function f makes a dance like this, say, where it keeps blowing up around a point, and let's call this point A or B. Let's call this point B. Okay, and let's say this is A right there. So this is a function which is in this case positive and continuous between A and B, but it has when it gets closer and closer to B from the left, the function blows up, so it has a vertical asymptote at B. Okay, and let's say that I choose a point T in between A and B, and I consider the region that's under the curve above the x-axis and bounded by x equals A and x equals T. So we're gonna have an area here. Now, if we let T get closer and closer to B, then we are discussing this region over here, which is an unbounded region because the function blows up and it has a vertical asymptote at B, right? This is unbounded region, but in a vertical way, right? In a vertical direction. So in the first type that we discussed, we had we had an unbounded region, but it was in a horizontal direction because the length of the interval was infinite. And here we have infinite or unbounded in a vertical direction, correct? Now, if this pink region, as T gets closer and closer to B, if this pink region gets closer and closer to a finite number, then we refer to this as being the region or the area of the region below the curve, to the right of A, to the right of the line x equals A, and to the left of the line x equals B, and above the x-axis. Okay, so let's write the details. So the pink area is the integral from A to T f of x, if you call this function f of x dx. So if this guy approaches a finite number as T approaches B from the left, right? So in other words, we're talking about the green area as being a finite thing. Then what we do is we say that that area, that green area, is that number, and we write that the integral from A to B, right? From A to B, f of x dx, we define it to be the limit as T goes to B from the left of the integral from A to T f of x dx. Okay, so if those pink regions, as T gets closer and closer to B, if those guys get closer and closer to a number, in other words, if this limit exists, then that's gonna be referred to as the area of that region, and it's gonna be denoted by the symbol integral from A to B f of x dx. So this is an improper integral, right? This is an improper integral over a finite length, over an interval which has a finite length. But don't forget, at B, this time I have infinite discontinuity, right? So that's improper because of that. Okay, so let's read the definition that pertains to this. So it's a definition of improper integrals with infinite discontinuities. if the function f is continuous on a to b and is discontinuous at b, any type of discontinuity, so we discussed the infinite discontinuity, but it can be any type of discontinuity, then the integral from a to b f of x is defined to be the limit as t approaches b from the left of the integrals a to t f of x dx, provided this limit on the right side actually exists as a finite number, as discussed above. Similarly, we're gonna define if we have discontinuity at the lower bound a. So we're gonna do the same game. Now we're gonna approach a from the right, and we're gonna discuss the integral from t to b f of x dx. Provided this limit exists as a finite number, we're gonna define it to be this improper integral. And as usual, if the improper integral is so if the corresponding limit is convergent, then the improper integral is gonna be called convergent. Otherwise, it's gonna be called divergent. So if the corresponding limit doesn't exist as a finite number. Okay, so we call it divergent. Okay. All right, and the last part C, if you have a discontinuity at a number C between A and B, not at the endpoint. So in part A, we had discontinuity at the upper endpoint, right? In part B, we had discontinuity at the lower endpoint at A. In part C, I have discontinuity somewhere between A and B. So you don't have discontinuity at the endpoint, at any of the endpoints. So you have somewhere between A and B a point of discontinuity. And if the integral from A to C f of x dx exists or is convergent, and the integral from C to B f of x dx is also convergent, then we say that their sum, or we write so we write the sum of those two to be equal to that integral from a to b f of x dx. So we denote that by the sum of the two. So we denote the integral. This is still improper integral between a and b f x dx, because you have discontinuity between those 2 points, right? This is not an ordinary integral, because I have discontinuity somewhere in between a and b. So we define that guy to be the sum of those 2 pieces, from a to c and from c to b, where each one of those is also improper, but provided they both converge, we define that guy to be their sum. Okay? Alright, so let's do an example. Let's do example 5. Find the integral from 2 to 5 dx over square root of x minus 2. So this is example 5. And here we need to evaluate the improper integral from 2 to 5, 1 divided by square root of x minus 2 dx. It's worth noting that this is actually an improper integral, right? Because we have discontinuity at the lower bound. At the lower bound in this case, which is 2, right? 2 is not part of the domain of this function. Okay? So technically, the function is going to look like, if this is 2, this is line x equals 2, the function is going to be like this, right? And we're trying to find technically the area from here to 5. So this whole thing. Okay? Just to put things in perspective. So this is definitely an improper integral, and what we're trying to do is we're trying to find this this area which is infinite in a vertical direction. Okay. All right. So we're gonna use part B of the previous discussion or previous definition. This is the limit as t goes to 2 from the right, t to 5, integral from t to 5, 1 divided by square root of x minus 2 dx. Okay, and what's the integral from of 1 divided by square root of x minus 2? This is equal to, so what's that again? This one here, primitive of 1 divided by x minus 2 to power half, which means if you want to take it upstairs is x minus 2 to power negative half. You can do just a simple substitution here. What you're gonna get is 2 square root of x minus 2, and this is going to be between t and 5. Okay, so this is then equal to limit of that. This guy evaluated at 5 is 2 square root of 5 minus 2 minus 2 square root of t minus 2. This is 2 square root of 3, right? And this is a constant with respect to t, so 2 square root of 3 minus the limit as t goes to 2 from the right, 2 times square root of t minus 2, right? 2 times square root of t minus 2. And what's that limit? What's this limit? This is 0, right? As t goes to 2, t minus 2 goes to 0. Square root of 0 is 0. So this is equal to simply 2 square root of 3. Correct? So this area that I was discussing at the beginning of this example happened to be 2 square root of 3. Alright. Let's go now to the previous page. And let's now do example 6. We need to determine whether this integral from 0 to pi over 2 sec x dx converges or diverges. So let's go to that page and do it. That's example 6. And we need to evaluate the improper integral. So from 0 to pi over 2 secant x dx. It's improper because secant is continuous between 0 and pi over 2, right? Remember, secant is 1 over cosine of x. It's continuous between those points, but it has pi over 2. At pi over 2, the function secant has a vertical asymptote there, right? So it's discontinuous at pi over 2. It has an infinite discontinuity, to be more precise. And this is equal to, by the previous definition, and this is part A of the definition, the limit as t goes to pi over 2 from the left, right? So pi over 2 from the left, the integral from 0 to t sec x dx. This is the limit as t goes to pi over 2 from the left. The primitive of secant is ln of the absolute value of secant x plus tangent x. We discussed this a while ago. And this is taken between 0 and t. Correct? Alright. And let's evaluate this at t. What do we obtain? So limit as t goes to pi over 2 from the left, ln of secant of t plus tangent of t minus ln of secant of 0. What's secant of 0? Is 1, right? Because it's 1 divided by cosine of 0, which is 1, plus tangent of 0, which is 0. So ln of 1. And ln of 1 is how much? ln of 1 is 0, right? So this is a nice entity. How about the rest? How about the rest? Well, what do we know about secant of t as t goes to pi over 2 from the left? So let's change color here. So secant of t goes to what as t goes to pi over 2 from the left? Well, secant of t, which is 1 over cosine, certainly it's a positive entity, but it gets closer and closer. Cosine gets closer and closer to 0 as t gets closer and closer to pi over 2 from the left, right? While staying positive. So that's gonna go to 1 over 0 plus, so it's gonna go to 0 to plus infinity, correct? So one more time. Secant of t as t goes to pi over 2, well, as t goes to pi over 2 from the left, cosine of t goes to 0 plus, right? So cosine of t goes to 0 plus as t goes to pi over 2 from the left, right? And as such, secant, which is 1 over that, is going to go to 1 over 0 plus. So it's going to go to plus infinity as t goes to pi over 2 from the left. So that's exactly what I said over here. And then, how about tangent? Tangent t goes where as t goes to, or as t approaches pi over 2 from the left? Well, certainly this entity is positive because this is still in the first quadrant, right? This angle t is in the first quadrant. But since cosine is getting closer and closer to 0 and sine is getting closer and closer to 1, so this is going to approach 1 over 0 plus, which is also plus infinity. Correct? So what do we get then? We get that this entity as t goes to, or as t approaches pi over 2 from the left, this blows up and this blows up. As such, the sum is going to go to plus infinity, right? So this sum also blows up, and ln of something big, how do we graph ln? This is the graph of ln. If x increases, if x goes to plus infinity, the function is blowing up, right? So ln of something big is very big. All right, so this entails that ln of x goes to, actually ln of secant with absolute value, secant of t plus tangent of t is gonna go to plus infinity as t goes to plus infinity. One more time, because this sum actually blows up. Each individual summand blows up. Then the sum is blowing up, so ln of something that blows up also blows up, right? Ln of a large number is still large. Okay, so all this package is actually helping me to infer that this limit is equal to plus infinity, right? Is equal to plus infinity. So this package was needed over here. Okay. All right, so this is this example. So this is example 6. So we discovered that this integral actually is divergent, right? So it's divergent. All right, example 7. Evaluate this integral from 0 to 3 dx divided by x minus 1 if possible. So let's use this over here. So example 7, we're gonna integrate from 0 to 3 the function 1 over x minus 1. Correct? So this is based on the third part. Let me take you back to this definition. The third part of the definition above, if the function has a discontinuity at a number c between a and b, in this case 1 and 3, sorry, 0 and 3, so 0 and 3, the function here over here in this context, in our context, c is 1, correct? Because the function is 1 over x minus 1. So 1 is a point where the function has a discontinuity. And what we need to do is we need to find the integral from 0 to 3 fx dx. And since the function has discontinuity at 1, then we're going to have, if this is something meaningful, then this is going to be equal to the integral from 0 to 1 f of x dx plus the integral from 1 to 3 f of x dx, right? And if each one of them is convergent, then their sum is going to be the value of this improper integral from 0 to 3 fx dx, correct? So this is the definition, and that's what we're going to be needing. Keep in mind, to find each one of them, we're going to use one of the previous parts of this current definition. For example, if you wanna find this guy, then you're gonna need part A, right? And to find this guy, you're gonna be needing part B, correct? Because part A is about discontinuity at the upper endpoint. Part B is about discontinuity at the lower endpoint. So you get that. All right, so let's go back to the page we started at. This is example 7. So this one. So this is equal to, as we said, by part C above of the definition, this is from 0 to 1 dx divided by x minus 1 plus the integral from 1 to 3 dx divided by x minus 1. So I need to evaluate each of these improper integrals, and again, if each one is convergent, then their sum is going to be the value of this improper, and hence this is going to be convergent. And if any of the two is divergent, then this is going to be divergent, right? Because for it to be convergent, I need each individual piece to be convergent. So it diverges if any of the two fails to be convergent. All right, so let's call this guy I and try to find what this I is. So I is the integral from 0 to 1 dx over x minus 1. And as I told you above, to evaluate this, I'm going to need part A of the definition. So this is the limit, because I have discontinuity at the upper endpoint. So t is approaching 1 from the left. Integral from 0 to t, right, dx divided by x minus 1. Okay? And an antiderivative of dx over x minus 1 is ln of x minus 1. So you get limit as t goes to 1 from the left, ln of absolute value of x minus 1, and this is between 0 and t. Okay? And then if you evaluate this at t, you get ln of absolute value of t minus 1 minus ln of absolute value of 0 minus 1. We get that. Okay, what is this? What is this? Absolute value of 0 minus 1 is 1, right? This is minus 1 inside. Absolute value of negative 1 is 1. ln of 1 is 0. Okay? And how about that? How about this piece? Just this piece, the absolute value. This is 1 minus t. Why? Because t is smaller than 1, right? T is approaching 1 from the left, so t is smaller than 1. And if t is smaller than 1, then 1 minus t, and then t minus 1 is negative. Then t minus 1 is negative. And the absolute value of a negative number is the opposite of that number. And the opposite of t minus 1 is 1 minus t. Correct? So all in all, you get that this is equal to the limit as t goes to 1 minus ln of 1 minus t. Okay? So as t approaches 1 from the left, where does this go? Where does this go? This is approaching 0 from the right. One more time. If t is approaching 1 from the left, so t is approaching 1 while staying lower than 1, so t is smaller than 1 as we said here, that number is approaching 0, but is approaching 0 plus, obviously. And what happens to ln then? So ln is going to approach what? So if this guy approaches 0 plus, ln is going to approach minus infinity. Let me explain why. How do we graph ln of x? This is the graph of ln of x, correct? If I tell you that x is a number that's getting closer and closer to 0 from the right, if the input is getting closer and closer to 0 from the right, how about the outputs? The outputs are blowing down, right? So ln of something that's very small, very close to 0 while staying positive, so something like this, the corresponding values to the function ln are gonna blow down, so they're gonna be minus infinity, right? So at the end of the day, this limit is gonna be minus infinity. So 1, this improper integral at the end of the day is divergent. So this guy is divergent, And hence this is divergent. No need to find this. Even if this is convergent, right? Even if this is convergent, this improper integral, the one that they asked us to do, is going to remain divergent because one of the two pieces is divergent. So there is no need to do that. Since that diverges, that's going to also diverge, right? So this entails, let me keep it in blue. So this entails that this guy is divergent, having one of its one of the two corresponding improper integrals actually is divergent, right? So since this guy was divergent, correct? div for divergent. This is what we found. This is what we called I, right? Okay. All right. So the next example. So we did example 7. This one. By the way, if we did the following mistake, if we didn't pay attention and we realized that this function 1 over x minus 1 has discontinuity at 1, and we could have made the following erroneous computation. This is wrong, okay? I'm gonna write it and then erase it. We could have written the following, that this is equal to, this is without observing that this function has singularity or discontinuity at the point x equals 1. We could have made the following mistake, x minus 1, and this is between 0 and 3, right? So ln of 3 minus 1 is 2, minus ln of 1, 0. So we could have found ln of 2 as being the value of this integral, and this is completely wrong, right? Because this integral actually is an improper integral, and an evaluation like this would be completely wrong. Okay, so anytime you get an integral, ask yourself, does the integrand have any singularity or discontinuity on that interval, which is of finite length, 0 to 3 in this case. In this case, you're going to realize that yes, at 1, that happens. All right. Example 8. Evaluate the integral from 0 to 1 ln x dx. I'm going to leave this one actually as an exercise. So I'll leave this as an exercise. I'll tell you what the answer is, but I'll let you think about it on your own. The answer is -1. Okay? So please find this as an exercise. And what can be the interpretation of this? Well, ln of x is if this function, correct? This point here is 1, and this point here is 0. So this is 0 and this is 1. So what this is actually technically this part, right? Technically, you're trying to find this area. And since this can be thought of as the net area, so the absolute value of that becomes this area, which is 1. So you can think about this area as being 1. Okay? So after you find that this integral is actually -1, you can interpret this by saying that this region that's shaded in purple here is actually the absolute value of this, which is 1, right? All right. Here's another problem that I'm going to leave as an exercise, and it goes like this. Prove that this improper integral is equal to half this one. So I'm going to leave this as an exercise, and my hint here would be to transition from the left-hand side to the right-hand side, use integration by parts. Okay? All right, moving on to the next, to the last concept in this section. Let's read this small paragraph. So even though sometimes it's impossible to find the exact value of an improper integral, we would like to know simply whether it converges or diverges. So sometimes it's hard to integrate and find the actual value of a given improper integral, but it may be useful in the context that you are dealing with. to just understand whether this integral is going to be convergent or divergent. So in such cases, the following theorem, this theorem that I'm about to mention, is useful. Although this theorem is stated for improper integrals with infinite integration limits, a similar theorem is true for the other type, so for those improper integrals with infinite discontinuities. Okay, so what does the theorem say? So this theorem is labeled as comparison test for improper integrals, and it goes like this. Suppose that you have two functions f and g that are both continuous, and you have this double inequality. So g of x is greater than or equal to 0, but it's dominated by f of x for all x greater than or equal to a. So if you would like to have a picture attached to this to illustrate the situation, so something like this, maybe this is the xy plane, and let's say you have a function g that's defined on from a onward. So let's say this is a all the way to infinity. So the function g is somewhere, I don't know, maybe here. Let's say this is the function g, and the function f dominates g in the sense that it's always bigger than or equal to g of x on that interval, right? On that interval, so from a onward. So the function f may be something like this, right? And the assumption it stays on top of g throughout this interval from a to infinity. What this theorem is saying, if this happens, meaning if the improper integral from a to infinity f of x dx converges, so in other words, if you want to interpret this geometrically, if this area here, the green area, which is under the top curve, which is the function f, if this is finite, then the integral from a to infinity gx dx, which can be interpreted as the area under the curve, under the bottom curve, which is g of x in this case, so this area is also finite, correct? So if the area, again, this is not the proof of the theorem, I'm going to omit the proof, but at least this figure makes it plausible, makes it seem plausible. So one more time, if this happens, which means something like this, the area under the curve, under the top curve, which is f, the area under the curve f is finite, then it follows that the area under the bottom curve, which is g, is also finite. Okay, so indeed the figure makes it believable, right? Again, this is not a proof, and we're gonna omit the proof in this lecture video. Okay, and this is equivalent, actually, if you read this comment, this is actually equivalent that the failure of this, which means this integral being divergent, is gonna entail that this integral is gonna be also divergent, correct? If something, if a hypothesis implies a conclusion, then this is equivalent to saying that the failure of the conclusion must imply the failure of the hypothesis, right? So if this fails, then you're gonna get the failure of that. This is what the comment is about. Okay. All right. So let's do the following example. Example 10. Show that this integral is convergent. So this is example 10. We would like to show that this integral is convergent. And if you pay attention to this, if you try to integrate this, it's not easy to integrate. As a matter of fact, the primitive of e to power negative x squared is not an elementary function. In other words, it's not one of the functions that we know. Okay, this function is actually, this integrand is called the Gaussian function. Okay. Anyway, so, and the only way I know of how to integrate such a thing is to use polar coordinates, which will be learned in multivariable calculus, so Calc 3. Alright, so we don't know how to integrate this. We don't know how to find the exact value of that. yet we still have to show that it's a convergent integral. Okay. Well, what if this 2 doesn't exist here? If this 2 is not there, just pretend this 2 is not there, then this integral would be easy to integrate, correct? Right, because the primitive of e to power minus x is minus e to power minus x. So this 2 actually is bothering. I would like, how about we try to understand the relationship between e to power minus x squared, which is the current function, and e to power minus x. Let's try to compare this function with this function and see what happens. Why I'm bringing this function? Because if I had instead of x squared e to power negative x squared e to power negative x, then I would easily integrate the function, right? So what I'm gonna do is I'm gonna try to sense the relationship between e to power negative x squared and e to power negative x on 0 to infinity, right? I want to understand the relationship between the two from 0 onward. So I mean, to completely understand it, let's actually try to sense it first. And in order to do so, I'm gonna invoke the online software Desmos. So I'm gonna go to desmos.com and graph y equals e to power negative x squared, which is the red graph, and graph the function y equals e to power negative x, which is the blue graph, and try to understand, just have a feeling of what's going on between the two functions from 0 onward, right? From 0 onward, don't forget, from 0 onward. So if you take a look here, the red function, which is e to power negative x squared, actually dominates the blue graph, which is e to power negative x, between 0 and 1, and the domination is reversed after 1. So the blue one, which is e to power negative x, dominates the red graph. At least this is what the picture suggests, what the figure suggests. I'm not saying this is a proof. We're gonna show it algebraically, but you get a feeling of what's going on. Why this is not a proof? Because this, how can you conjecture that this keeps going forever, right? You cannot keep scrolling to the right forever. So the point is, you get a feeling and then you try to show it. So it looks like from 1 onward, the function e to power negative x actually dominates e to power negative x squared. Let's show it algebraically now. So let's go back here and show this algebraically. So for x greater than or equal to 1, according to the picture, we observe that e to power negative x is gonna dominate e to power negative x squared. Let's make the case. Well, if x is greater than or equal to 1, how about we multiply both sides by x? X is positive because x is greater than or equal to 1, hence it's positive. So if you multiply by such an x both sides, you get x squared is greater than or equal to x, right? This is by multiplying both sides by x. And x is positive here because it's at least 1, which is positive, correct? So which is positive, being bigger than 1 or equal to 1. Correct? So for such an x squared certainly is at least x. And then if you multiply both sides by -1, you have to reverse the inequality sign, right? So greater than or equal becomes smaller than or equal. So hence negative x squared is less than or equal to negative x. Again, why? Because I multiplied both sides by -1 by multiplying both sides by -1, which amounts to reversing the inequality sign because I'm multiplying by a negative entity, right? Okay, so we got this up to this point. So for x greater than or equal to 1, we have this domination, and then let's apply the exponential function with base e to both sides, right? The exponential function with base e to both sides, which is an increasing function, correct? How do you graph e to power y or e to power z if you think about this as being the z-axis? E to power z is is graphed as such, correct? So if you give me two numbers, so it's an increasing function. If you give me two numbers, a and b, so that a is smaller than or equal to b, e to power a is gonna be less than or equal to e to power b, because the function is increasing, correct? This is gonna be my a, this is gonna be my b. So e to power that is gonna be less than or equal to e to power this. That's what I'm saying. Okay, because the function e is the exponential function with base e is increasing. Okay, so we get that. So therefore, let me go back to purple. So and as such, e to power negative x squared is less than or equal to e to power negative x, since the exponential function with base e so which I mean e to power, right, ey or ez, is increasing, correct? So e to something, if you have an input that's smaller than or equal to another input, e of that input is gonna be smaller than or equal to e of the bigger input, correct? So what used to be small remains small. Very good. So isn't that what we observed on Desmos, this relationship? So for all x greater than or equal to 1, actually this happens. We sensed it by the from just looking at the graph, right? Just by looking at the graph. So from 1 onward, e to power negative x is bigger than or equal to e to power negative x squared. We sensed it using the graph, but definitely this algebraic discussion makes it correct. All right, so from 1 onward we have this domination, which means so therefore by the previous theorem, right? By the previous theorem, what do I mean by previous theorem? This one. By the comparison test for improper integrals, the f function, the top function is e to power negative x, and the purple function is e to power negative x squared, correct? So therefore by the previous theorem, we have that if the integral from 1 to infinity of e to power negative x dx, if the area under the curve, under the top curve, which is e minus x in this case, is convergent, then, right, then the area under the bottom curve, so e to power negative x squared dx, is also convergent, correct? This is what the previous theorem is states, correct? It's right there. So let's be very clear. Who's g in our context again? G is the e to power negative x squared, and who's f? It's the function e to power negative x. And who's little a? Little a is 1, right? Little a is 1. So I'm using this theorem with those 3 items. Let's actually highlight this over here. So by the previous theorem, and let's be very clear, with g of x, which is the smaller, the bottom one, so e to power negative x squared. F of x is the top one, which is e to power negative x. And little a, right? So these are the choices of f, g, and little a, which is 1 in this context, correct? So this is why you see from 1 to infinity. Okay? So I infer that this is convergent provided this is convergent. You're gonna ask me, oh, but the improper integral that's given, it's from 0, right? Well, sure, it's from 0, but listen, 0 to infinity, you can split it as from 0 to 1 and then from 1 to infinity, correct? 0 to 1, the definite integral from 0 to 1 e to power negative x squared. This is continuous function between 0 and 1. Certainly it has a finite integral. And then the problem becomes from 1 to infinity. This is why I'm just talking about from 1 to infinity. Okay, so we'll write the details just shortly, but just bear with me for a second. So let's understand if this is convergent. Let's understand if this is convergent. So further, this integral 1 to infinity e to power negative x dx, this is easy to evaluate, right? This is the limit as t goes to plus infinity 1 to t e to power negative x dx. The integral of this, as we said, it's easy. So limit as t goes to plus infinity, this is negative e to power negative x from 1 to t, right? The primitive of e to power negative x is minus e to power negative x, 1 to t, and that limit is what? Sorry, plus infinity here. So what's that? This is, if you evaluate it at the lower bound, if you want to lose the minus, e to power negative 1, right? E to power negative 1, which is 1 over e minus e to power negative t, correct? So one more time, when x is at the lower bound, e to power negative 1 becomes, which is 1 over e, at the upper bound it's e to power negative t. Okay, when t goes to infinity, what happens to this? What happens to this when t goes to infinity? This goes to 0 as t goes to infinity. So as t goes to infinity. Why? Because the function e to power negative x, this is how you graph e to power negative x or negative t, correct? And as t goes to infinity, as you are progressing into the future, the values of the function become closer and closer to 0. This is why this is happening. Okay, so we get this, and then what's the limit? The limit becomes just simply 1 over e, right? So it's 1 over e because this is 0. This goes to 0. Okay. All right. So long story short, this is a finite number. It doesn't matter what this value is, as long as it's finite. This is convergent. So this is convergent, and as such, this is going to be also convergent, right? So therefore, this integral is convergent, and hence this integral from 1 to infinity e to power negative x squared dx is also convergent, right? By the previous theorem. So by this thing, how about we label this something? How about we label this implication something? So how about star? So this is by implication star. So by implication, so by statement, I should say, maybe star. Okay. All right. So this is convergent, but as we said, the problem was I need to find whether the integral from 0 to infinity, if it's convergent or not. Keep in mind that I don't know the value of this integral, right? I didn't say that this value is equal to 1 over e. The value of this integral is 1 over e, but the value of this one, I don't know it. All what I know is that it's convergent up to this point, correct? So I'm not claiming that the values of the two integrals are the same. All right, so back to the actual problem. So finally, the integral from 0 to plus infinity e to power negative x squared dx, you can write this as the integral from 0 to 1, right, e to power negative x squared dx, plus the integral from 1 to plus infinity e to power negative x squared dx. Correct? Why you can write this? you can write here, this is the limit from 0 to t, where t goes to infinity, correct? And then goes from 0 to 1, and then from 1 to infinity. So probably I should write all the details. Okay, so this is the limit as t goes to plus infinity, 0 to t, e minus x squared dx, right? And now let's pay attention just to this part. This part here is the integral from 0 to 1. If you take t sufficiently large, 1 is going to be before t, right? Plus the integral from 1 to t, correct? So you get, this is equal to the limit of t goes to plus infinity of the integral from 0 to 1 e to power minus x squared dx, plus the integral from 1 to t e to power negative x squared dx, correct? So this is the orange part. And then since this guy is a constant with respect to t, so this is independent of t, right? So this limit, you can split the limit of that constant independent of t. So this constant is itself, so 0 to 1 e to power negative x squared dx, plus the limit as t goes to plus infinity, the integral from 1 to t e to power negative x squared dx. Okay, so one more time, the limit of that, because this guy is independent of t, it's a constant with respect to t, so the limit of this remains itself, and plus the other limit, right? And what is that guy? This is the improper integral from 1 to infinity, right? So we get exactly as I wrote at the beginning of this, but these are the details. Okay, so you get that. And then now put things together. What do we know about this? What do we know about this? This is convergent, right? This is convergent. We know this from above, correct? This is from here. Where is it? It's right there. This is convergent. Okay. And what do we know about this part? What do we know about this part? Well, this is continuous on 0, 1. This function is continuous on 0, 1. Correct? This function is continuous on 0, 1. And hence its definite integral between or over 0, 1, it's going to be certainly finite. I don't need to know what the exact value of this, but certainly this is finite because I'm integrating a continuous function over if an interval of finite length, right? The function is continuous there. Certainly this is going to be finite. So at the end of the day, what do you get? At the end of the day, you get that this integral that you wanted, this integral is actually the sum of two integrals, this one, and they're both finite. I don't know their values, but I know that they are finite, both of them. And as a result, you get that the desired integral is also finite. So as a result, the desired integral, the improper integral from 0 to infinity e to power negative x squared dx, must be finite, in other words, convergent, right? Okay. All right, so let's go back to the earlier page and let's do the last problem. That would be example 11, right? So this part. The question is, does the integral from 1 to infinity 1 plus e to power negative x over x dx converge? So the question is, does it converge or not? So let me take it back to the very last page and treat it there. Okay, so this is example 11. And the question is, does this integral from 1 to plus infinity 1 plus e to power negative x over x dx converge or not, right? So that this numerator 1 plus e to power negative x, so 1 plus e to power negative x, since e to power negative x is positive for all x, certainly this guy is greater than 1, right? Certainly this guy is greater than 1 for all x. for all x and r, let alone for those x's which are from 1 onward. Correct? So this holds for all x and r. Now, for x being greater than or equal to 1, we have 1 plus e to power negative x divided by x, right? Since the numerator is greater than 1, and the denominator is positive, because being bigger than or equal to 1, so that guy downstairs, which is at least 1, certainly is positive. So you get that this is bigger than 1 over x, right? So one more time, since 1 plus e to power negative x is greater than 1 for all x, if you let x be positive technically, so if you let x be bigger than or equal to 1, because over here x is supposed to be greater than or equal to 1, so certainly such an x is positive. So if you divide now both sides by x, the inequality remains true. Correct? So we have that this holds. Okay. Also, what do you know about the integral? What do you know about the integral from 1 to infinity of that guy? So what do you know about the integral from 1 to infinity of this guy, 1 over x dx? Well, this is the limit as t goes to infinity, 1, right? 1 to t, 1 over x dx, which is ln of the absolute value of x, right? So ln of the absolute value of x. I don't need to put the absolute value here because I'm integrating between 1 and t is supposed to be large, right? So t is going to infinity. So I get this. And that's limit as t goes to plus infinity, ln of t minus ln of 1. ln of 1 is 0, right? ln of 1 is 0. So this is limit as t goes to plus infinity, ln of t. And what happens to ln of large values, right? As t goes to infinity, ln of t is gonna go to plus infinity as well. Correct? So this integral is divergent. So this integral is divergent. Correct? And since 1 over x is smaller than this guy, certainly this is positive, right? For x being bigger than or equal to 1, certainly this is positive. I can employ that theorem that I just discussed, the comparison theorem. Let me take you back there. I'm gonna apply the equivalent statement of that. Technically, I'm talking about the comment, right? So g of x, I'm taking it to be 1 over x, and I'm taking f of x to be the other function, which was 1 plus e to power negative x divided by x. Correct? So 1 over x is smaller than or equal to that. As a matter of fact, it's strictly smaller, but if it's strictly smaller, certainly it's smaller than or equal to this guy. And this 1 over x is positive, and hence it's non-negative, right? So this double inequality here holds for my choices of g and f. And also, what did we get about this integral? By the way, a is taken to be 0 here, right? In our discussion. So the integral from 0 to 1. It's 1. So the integral from 1 to infinity of 1 over x, g of x is 1 over x dx. We found that this is divergent. So what can we infer by this theorem? We infer that this guy, where f of x is 1 plus e to power negative x over x, is divergent. Correct? So let's go back over there and conclude. So therefore, thus, by the comparison test, this is by the comparison test, right, above, we get that the integral from 1 to plus infinity, 1 plus e to power negative x divided by x dx is divergent, correct? And this is by the previous theorem. which is the comparison test, and by this I mean the equivalent statement of the comparison test, which was labeled as a comment above, right? Okay, so this completes the current section.